Section 5.1, example 3, determining convergence and finding limits. So for each of the following sequences, determine whether or not the sequence converges. If it converges, find its limit. So difference between converges and diverges. Converges means that it ends up going towards a specific value. So if we look at a graph and we looking at 1 over x, from the right side, we have this graph here. We would say that this converges to 0. As our x values keep getting larger and larger and larger, this gets really, really close to 0. So it gets close to 0, it doesn't end up going anywhere else. Whereas if we were to look at a parabola on the right side, as x gets completely larger or continuously larger, the function ends up going to infinity. It's not predictable. We're not ending up at a specific place or near a specific place. We just keep going off into infinity. So that's the difference between converges and diverges. Now with the sequence, values, as we keep adding and adding and adding everything up, if it converges if it ends up at a specific value, it diverges if it just goes off to infinity. So for this problem, we could use a limit of a sequence test. So what we do is we assume that this sequence here is a function and we just find the limit of that function. So we'll call this a sub n, and we'll look for the limit as n approaches infinity of a sub n. So we're going to find the limit as n approaches infinity of 5 minus 3 over n squared. And now looking at this, we could automatically plug infinity in. So as our numbers, or as n gets continuously larger, this value ends up going to 0. So it becomes so small that we can't add anymore. The values become so tiny and insignificant that we just end up looking at the number 5. So now for our sentence here, we would say therefore, because our limit told us that we end up at the number 5, we say that therefore a sub n converges to the number 5. That's what we state here. And there we go. Let's take a look at this next one. Oh, and I made a mistake right here. So that should be to the power 4. So again, we're going to take the limit of a sub n. Let's move this down a little bit. We're going to take the limit of a sub n. So the limit as n approaches infinity of this function, 3n to the power 4 minus 7n squared plus 5 over 6 minus 4 over n to the power 4. And from here, we're going to multiply by the highest degree, which happens to be the same in the numerator as it is in the denominator. So 1 over n to the power 4. And multiply that through. We end up with the limit as n approaches infinity of 3 minus 7 over n squared plus 5 over n to the power 4 over 6 over n to the power 4 minus 4. So as n approaches infinity, this goes to 0, this goes to 0, this goes to 0. And we're left with a negative 3 over 4. So we say that this converges to negative 3 over 4. So therefore, a sub n converges to negative 3 over 4. There we go. And lastly, part C. We take the limit That's all we have. All right, so part C, we take the limit as n approaches infinity of made a mistake there. So this is actual C. D we'll do here in just a minute. So what we're looking at here is the limit as n approaches infinity of 2 to the power n over n squared. And there isn't much that we could do here, so let's just evaluate. We notice that the numerator goes to infinity, denominator goes to infinity. We could apply L'Hopital's rule. And I see now that I'm using the wrong color. Much better. Yeah. All right, so we could use L'Hopital's rules to take the derivative of the numerator and the derivative of the denominator. And the limit as n approaches infinity of derivative of 2 to the power n is still 2 to the power n times ln of 2 over here we have 2n. Apply the limit, we still have infinity to infinity. Let's apply L'Hopital's rule again. The limit as n approaches infinity. Here we have 2n. I'll write it like this, ln of 2 squared over 2. And this part entirely goes to infinity. So we don't end up at a specific value. So we would say that the sequence a sub n diverges to infinity. So our first diverge. And now that we see what a diverging sequence looks like, let's look at this one. So the limit as n approaches infinity of 1 plus 4 over n to the power n. And here, let's see. What we could do is let this sequence be y. So let y equal, because we have this exponent. One way that we could bring the exponent down to evaluate it is to turn it into a log, because exponents come down as coefficients. So we're going to do that. We're going to set this equal to a function to the power n. We're going to take log of both sides, or natural log. So ln of y is equal to ln of 1 plus 4 over n to the power n. So that way we could grab that exponent and bring it down to the front as a coefficient. We have ln of y is equal to n. And all the while we're taking the limit as n approaches infinity. So the limit as n approaches infinity. And the limit as n approaches infinity. 1 plus 4 over n, oh, natural log. Ln of 1 plus 4 over n. And now that we have that, all right, so now that we have that, what we could do in order to evaluate this part right here is turn it into a fraction. So instead of n, I'm going to write this as 1 over n down here. So that's going to be the limit as n approaches infinity of ln of 1 plus 4 over n over 1 over n. We apply the limit, and this ends up being 0. So we have ln of 1 equal to 0, and this part ends up being 0. So what we have is 0 over 0. And we're able to apply L'Hopital's rule here. So let's take the derivative of both. So that's a limit as n approaches infinity of the derivative of the numerator is just going to be what we have on the inside. 1 plus 4 over n times the derivative here, because we have n applied right there too. So that is going to be times 4 to the, okay, so we have 4, we have n minus 1. So 4 times x to the negative 2 and negative here. So that should be a negative 4. There we go. And down here we have our n to the negative 1. So that's going to be negative 1. We're multiplying that times n to the negative 2. We have that. So now let's look at everything that divide, not n, not x. So this should be n. All right, so n to the negative 2, those divide out. The negatives divide out here. And let's see what we have. The limit as n approaches infinity of 4 times, oh, and all of this is over 1, under 1. So we have 4 times 1 minus, or 1 plus 4 over n. Much better. So this goes to 0. We end up with 1 over 4, or 4 over 1, which is just 4. We ran out of room down here. Let's move this over. So we ended up with 1 over 4. But as we move all of this down, ln of y, ln of y, ln of y, we end up with ln of y equal to 4. And from here, we could apply some logarithmic properties. And all ln's are of base e. So we have e to the power 4 is equal to y, or y is equal to e to the power 4. And because y is equal to e to the power 4, we kind of look at what y was. Over here, we set y equal to the limit of all of this. So the limit of all of this ends up being e to the power 4. So Euler's number. So what we could say is, therefore, this sequence a sub n converges to e to the power 4. And this is actually a property that we end up, well, we kind of just learned about it. So this is actually a property that we could apply whenever we see something of this form. We automatically say that it's e to the power, and we could call this, let's call this omega. This ends up equaling e to omega, whatever omega ends up being. And there we go. If you have any questions, please feel free to ask. Otherwise, bye.